Hello, everyone. Today we have Rachel Cummings. She's an assistant professor at Columbia University. Prior to Columbia, she was an assistant professor at Georgia Tech. She received her Ph.D. from Caltech, and her supervisor was Katrina Ligett. Her work focused on data privacy and its connection to machine learning, data science, and algorithmic economics and optimization and statistics, and public policies. She has been a recipient of several awards, including NSF CAREER Awards and DARPA Young Faculty Award. We're very happy to have her today. And today she will talk about her work on mean estimation with user level privacy under data heterogeneity.
Thank you. And I'm super happy I can be here, at least virtually, and see like so many friends. It's very nice to join like a Boston area privacy things, because I think this is the most like a privacy critical mass in one place I could possibly imagine, and so that's extremely fun. I'll be talking today about joint work with like a Vitaly Feldman, Audra McMillan, who is here, I see. Hey, Audra. And Kunal Talwar. All of them are at Apple on the privacy team. And this is some work that came out of my consulting at Apple last year. So I will start with a extremely hypothetical example. Imagine that a company that makes smartphones wants to predict the frequency of words and texting or kind of emoji on their keyboard. And they know a few things about their population. So they know that different users may have different patterns of texting in terms of how frequently they use that particular words, but I can also say that we might have kind of user specific data like distributions. And then we also know that different users may have different levels of use in terms of texting. They may type different quantities of words every day, which means that I'm also going to have varying quantities of a per user data. And they also know that the content of one's texting might be highly sensitive. And so they want to give formula privacy protections for that data. So I'll start with a model and then we'll kind of go from there. And so let's say the goal is to do mean estimation. And you can imagine I want to estimate the frequency of a particular word being typed. And so this is going to arrive as a Bernoulli samples where there's some a probability of a user typing a particular word, and for each word they type it'll be translated either into a 0 or 1 in terms of me counting the a frequency of that word. So I'm going to say that each user I is going to have KI data points, sampled IID from their personal data distribution, DI that's going to be Bernoulli with a parameter PI. And so again, heterogeneity comes in two separate ways. We're having different quantity of samples from each person, and we're also having their samples come from different distributions. And our goal is to estimate the And our goal is to estimate the a population level mean. And so to make that formal, we're going to have to talk about how these parameters PI relate to each other. And we'll say they're all going to be sampled IID from some kind of underlying population level meta distribution D star. And we're going to assume virtually nothing about this. We're just going to say it has some arbitrary support. And so in this case, because we're talking about talking about like Bernoulli parameters, it must have like a support 0, 1, and it has some mean and some variance, and we don't know them, but we would like to estimate P. So we're going to assume the samples and the parameters are going to be unknown to the analyst, but these like KIs are known. We're going to talk on the very, very last slide about how we can relax this. But like for the entire talk, we'll be in this framework. And the goal is going to be to construct a private estimate of P in a way that is unbiased and is going to have small variance. So now we'll start by considering this in the kind of easiest case possible. Imagine that we don't care about privacy, and I know all of these parameters, P, sigma squared, and of course, if I know P, then I don't have to like estimate it. But let's like imagine that we do and see how this kind of like estimation procedure might go. So first, I can just like compute each user's empirical mean of their samples. And I'm going to let sigma squared I be the variance of this like pi hat, and so this is going to like depend on the variance of the underlying population distribution and on the number of samples. And so I can just like compute this, and the analyst can then minimize variance using just a kind of like weighted average, or alternatively a kind of like linear estimator that will weight pi hats inversely proportional to their variance. And so this will look something like this. And so I'm just going to take like an average where the weight is going to be inversely proportional to the variance, and I'm then going to like normalize to kind of like make sure that my weights sum to 1. And so this is unbiased, and it has like the best possible variance. And so this is kind of how we're like ideal case. But of course, we can't actually do this because we don't know this, and we have to like estimate this based on the data. So now let's do a slightly more challenging warm-up where we in fact don't know parameters of this underlying distribution. And we'll first show that we can like compute this using like parameters of this underlying population level distribution. I'm not going to prove it, but this is like, homework you might give in a kind of like, undergrad probability class, but it's true. And so this tells us that kind of like if we have a good estimate of the mean and the variance of this like a population level distribution, I can then like plug them into here, and I can have an estimate of these kind of like individual level variances, and I can then plug in that to like compute the optimal weights. And so we see a process here, but the problem is that like in fact I have to have like reasonably good like estimates of these things if I want to plug them in to this, and then plug this into the weights estimate, and then use the weights to like to kind of perform this like a total estimation. And it turns out we can do this. And the general idea is to like split users into 3 groups. And I'm going to like separately compute initial estimates of the mean, initial estimates of the variance, and then this kind of final estimator. And you could compute kind of like all 3 things across all people, and this is fine. You then have to worry about kind of like adaptivity, because you're going to use these first 2 estimates as like input into the final estimator, and you can control for that, but it's kind of annoying. And this is a warm-up, allegedly. And so let's just say I'm going to split the population, and I'm going to compute these things separately, so they are going to be independently computed on some fresh samples. And our high-level approach is going to be this. It's kind of ugly, but I will talk you through all the parts. So we're first going to use one sample here from a constant fraction of our users. And that constant fraction here is going to be 10%. You can pick a different constant. You do have to have a constant fraction if you want this initial mean estimate to be of kind of high enough quality to give you a good estimate. In this process, how we push things through, and a 10% is magic, but it's clean. And we're only going to take one sample from these users, and these are going to be users that have the least data. I think I forgot to say we're going to sort users by the quantity of data they have, or by their KI. And so I'm here taking the kind of highest numbered KI users, which means they have the least data. And so because these are the users who have kind of very few samples in general, if I were to use their PI hats, they would be very noisy estimates because they have small amounts of data. So we're going to kind of waste them, quote unquote, by just taking one sample, and I'm then going to use this as my kind of initial mean.
Rachel, I have a question. So the KIs, that's the amount of data each person has, right?
Mm-hmm. Yeah.
And that's unrelated to their data in somehow, right? So we're thinking of the KIs as fixed a priori.
Yes. They are fixed, and they're also going to be independent of the data content. You can certainly imagine that that's maybe not really true, but that's a little bit harder case to think about. And so for now, for this entire talk, we're going to think about the quantity of data that you have is going to be independent of the content of your data, and they're just fixed up front in some way. Yeah.
Thanks.
Yeah. And so then I'm going to compute the initial variance from the log n users who have the most data. And because they have the most data, they're going to have the most accurate estimates PI hat. And I'm going to use this to kind of empirically estimate variance. Again, you can have some constants up front. We're going to be pretty loose with our constants in this entire talk. But as long as you take theta log n users, here it's fine. And we're then going to use these initial estimates to kind of plug in and to compute initial variance estimates, and then compute optimal weights on the remaining users. And importantly, we still have a constant fraction of our data here. And we're then going to use these weights to compute the final estimate. So this is basically a pipeline, it's a process. And this process is one that we're going to use in the private case as well. Yes. And then we can show that the variance of this estimator is within a constant fraction of the variance of the ideal estimator, assuming you have enough people and D star is kind of well behaved in some sense. So this was supposed to be a warm up, and it turned into not really, or perhaps we feel very warm now. And we haven't even talked about privacy yet. And so now we're going to make this even more complicated by requiring their estimator is computed privately. And I'm going to assume for this,
Rachel,
audience.
can I
Oh
ask
yeah.
a question before we get, so
Yeah.
is that the estimator you presented?
Yeah.
Is there a sense in which it's like the optimal one? This one, right? Is there a sense in which this is optimal? You know, the best thing you can do, or
So
something like that?
So yes, with an asterisk. So the asterisk is a kind of in general, this thing is the best you can possibly do if you know all the parameters, but you still want to kind of like estimate based on samples. I'll talk at the very end about, so basically as a preview, we're going to kind of like add privacy into this process, and the same overall structure is going to happen in the private case. We're going to have to add like, a bunch more details, and we're going to have a claim at the end of the private part that basically says our estimator is within a constant factor of the like a private ideal. And you might ask, how good is this private ideal? Is it optimal in some sense? And we will show, I think like in this talk, I won't show, but I will claim that the like, the like a private ideal where you have distributional knowledge is within like a polylog factors of the optimal.
All right, great, thanks.
Yeah. So I'm assuming for this audience, I can totally skip the next couple slides where I like define a differential privacy. Is that true?
Yes.
Cool. So good. Okay. It's so nice. I can skip these. And like, the only thing I do want to point out is that we are going to be talking about user level privacy, and that is much harder to achieve because we may have like a different people contributing like a different like a quantities of data. And so if I want to protect user level privacy, I have to consider changing like the entirety of one person's data. And since different people contribute different amounts of data, that is going to be one further challenge. And if I didn't care about kind of like user level privacy, and if I only cared about event level privacy, I could just like take the empirical mean and like I'm basically done. Okay, good. So this is, Salil, yeah.
Yeah, Rachel, the abstract mentioned something about the federated setting, but I have missed in your presentation now, where was the federated setting?
Yeah, good. So I think the abstract is slightly outdated / slightly ambitious. So you can certainly imagine this being kind of like extended into the federated setting where we're saying, let me see if I can go back, like, here, really like, if I know how to sort people, I can just tell them if you fall in like this group, send me 1 point. If you fall in like this point, this group, send me like your empirical mean. If you fall in this group, then you should also send me like your empirical mean. And so in some sense, this can be done in like a federated like setting, but I wouldn't really claim this is doing federated learning.
Got it.
Yeah.
Thanks.
Yeah. Thank you. Yeah. And I think that we went back and forth on some abstract. I think the one that I sent is maybe a slightly outdated version that was more kind of like, ambitious in the federated direction, but more honest abstract would talk about and may include possible future applications into the federated setting. Yeah, thank you. Okay, so here our goal is going to be to like privately estimate P, and the approach, and this will also serve as an outline of the talk, will be to first like construct an estimation framework in the same way that kind of like parallels what we saw in the kind of like a non-private case, how we're gonna split people, compute the initial means and variances, compute some more stuff, and then compute the kind of weighted mean. And we're for here going to assume that I have these good intermediate estimators of the mean and the variance, and I won't kind of like worry about where they come from, but I will like assume that I have them. And then I will talk about how we can achieve them. And then I will talk very briefly about these kind of like optimality claims. And really 2 is going to be pretty brief as well. And we're going to spend like, the bulk of our time on 1. So now let's kind of continue in a parallel thought experiment in the private case. Imagine if I had like complete information about the distribution. So then I can like continue in this way. I'm just going to do like the same thing as before, have my same weights, and I'm then just going to add Laplace noise. And here in this case, because of the weights, like the maximum one person's data can affect this outcome. It's kind of like the largest possible weight a person might have. But a problem is that like the max weight might be too large, because like imagine a case where kind of one person has like a ton of data and like everyone else only has one sample. So then basically that person's weight is going to be close to 1, and we're trying to like estimate something in the range of like 0, 1, and so this may not really provide me like an accurate estimate. So
Rachel, can I ask a question?
Yeah.
Sorry, I'm just talking right here.
No, good.
Raise my hand, but why is the sensitivity the maximum weight? Wouldn't it be something like the maximum weight divided by ki, like wi star over ki or something like that? No.
Yeah.
Sorry, user level. I blanked for a second.
Yeah.
All right.
Yeah.
Now I'm again.
Yeah. And that's in fact why it is much harder in that kind of like user level setting, because kind of like a lot of these challenges don't exist if you're talking about like event level privacy.
Right.
Yeah. So I'm going to solve this by having like an upper bound on the weights. So maybe I'm going to like cap my weights at some t, and then I can say, well, the kind of like maximum amount anyone's data can affect this with this cap is t. And I will point out in the way that kind of like Audra always says, and I love, like I am telling a small lie here, because in fact, these weights don't actually achieve this. So you really want like the maximum weight to be t, but I'm not really having that here because I also have to like normalize because I want the weights to sum to 1. And so you actually want to have like, a bound on the max weight and also have the weights sum to 1. And this in fact doesn't do it. But to write this precisely is kind of like more ugly than it is interesting. And so I'm going to like continue telling a small lie during the talk, and I will briefly at some point flash up the like complete algorithm, and you'll see things don't exactly match, and it's because of this small lie. But it's basically for your eyes and for your sanity during this talk.
Is it the case that the form of the expression for the weights is correct? It's just that like the sensitivity is then a little different.
Yeah. And so then you can no longer have t playing the same kind of like intuitive role that it does as like a maximum threshold. So like this is fine, but then kind of like this t is not correct anymore.
Right. Okay.
Yeah. 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 And so here intuitively, T as a threshold is like a balancing, a trade-off between like the variance of this estimator, which is going to be minimized by having like higher weight assigned to those that have more samples and therefore smaller variance, and also like the variance of the noise, which is going to be minimized by kind of giving everyone the same weight. And so that's the role of this like threshold T. And you can just write that down as like optimization problem, and you can kind of express variance of this thing, and then you can just solve for the optimal T star. And I'm not gonna show you that because it involves a small lie that I told, but you can do it, and you basically have this kind of like single dimensional optimization problem, and so it's fine. One more thing you can do to kind of like reduce sensitivity and therefore like reduce noise to be smaller could be to like truncate these estimates pi hat to live in some range AI BI that is going to be strictly smaller than the full space 0, 1. And so we know, assuming everything is going to be well behaved, pi hat should be close to p with high probability, assuming enough samples, assuming like, D star is nice and so on. And so like if you choose AI BI to be basically like the true mean, like a plus or minus concentration terms, then you can say with high probability, even if I truncate pi to like be in this range, I'm not actually going to like truncate the content of my estimators, but I will be able to say with like a pretty high like confidence. And in fact, I can say with like a complete confidence that my like a truncated pi hat is going to be in this range. And I can say with high confidence, it will not actually have like changed the content of my estimators. But the problem is that we like haven't assumed anything about D star. So we're going to do this kind of weird thing where we're going to write down like a concentration inequalities about a distribution that we have not defined. And I want to point out they're kind of doing like the same thing that we do in kind of like regular concentrations, but I just like haven't like explicitly said D is blah. So we're going to assume there exists a known function f that is very highly parameterized, that basically like describes high probability concentration of this empirical mean pi hat around the true mean p. And we're going to say that I want with high probability, like for all of my users, I want like pi hat to be close to p. How close? Something that like depends on the tail of like D star, and this expression will depend on the number of samples I have and on my D star and on the number of like users, because I want this for all I, and on the variance and on beta. And so again, I'll say this is like the kinds of things that we are very used to saying if I say like, D star is a Gaussian or it's a plus or it's a binomial. And we're very used to seeing things like this, but I just like haven't said what it is because I want to keep this fully general. And we're also going to assume in this kind of like ideal case, full information, this function is known. And when we move into kind of like estimating things, we're going to assume that like the function is known, even though all of its inputs, in particular, sigma squared p, is not known. And so again, if I say, I think this is a binomial, then I can like, plug in a like a specific form of this. We're just trying to kind of like avoid doing that. So then I can take this And I can then add kind of like one more level. And I'll again say that I'm doing a small lie here. And we're going to add one more step, which is that we're also going to like truncate estimates. And in particular, I'm going to make sure all of my like PI hat lie in the set, the AI BI, and this allows me to also like decrease the range of my noise because I know PI hat truncated is going to be smaller, and I'm going to pick AI hat and BI hat to be basically like the true mean plus or minus these like concentration terms. And again, like I'm doing this ensures that my like truncation won't affect estimation most of the time, except for some outliers, but those are kind of like unlikely anyways. So now I have figured out how I can do this like estimation if I know all the parameters that I wish to like estimate. And so now let's move back into this like unknown parameter space and figure out how I can do approximately this if I don't know all my input parameters. So again, it's doable. I feel like, calling this easy is not quite fair. I'm like the person being like, and the proof is left to the reader as a trivial exercise. So I put a like, easy with a question mark. It is doable if you know everything. But of course, with privacy, we now have to estimate a bunch more stuff, and we have to estimate like the weights as before, and the threshold, and these like truncation parameters. But it turns out all of these, if you know like the mean and the variance of this meta distribution D star, then you can like compute these. And so we saw this is true for the weights. It turns out to also be true for the like threshold, which I haven't shown you. And then we saw, assuming you know this like a general function f, if you were to know the variance, then you can just like plug in that value to learn these like truncation parameters. So we really just need initial estimates of these two things. We also have to have them be private because we're going to like compute them based on the data. We can't just add privacy at the end. And so we have to also like privately estimate these things. And we're going to go through the same framework as before. We're going to assume that we have private accurate estimates of these things, and we're then going to show how this like estimation works. And I apologize in advance for the next slide. It's going to be horrible, but in fact this is the like complete algorithm, and don't be scared. And also my lies will show. But importantly, I want to point out they're basically going through like the same procedure that we had before in the non-private case. And in particular, we're going to start by doing these initial and now private estimates of the mean and the variance on some like a partition fraction of our users. Oops. We're then going to use those initial estimates to like compute an estimate of the initial variance. And we're then going to use those estimates of the like individual variance to like compute the optimal weights. And we're then going to use those weights to like compute the final estimate. And so basically going through the same process as before, only we have a few changes. So we're first going to have to like estimate our like truncation parameters using our initial estimates. We're also going to have to like compute the optimal threshold on the weights T star. And we're then going to have to add noise for like privacy, and that is going to scale in a way that like depends on kind of all of our other parameters. So again, like the framework is the same, and we just have to change a whole bunch of these like intermediate details. And like the main result is that this estimation procedure is going to be epsilon delta differentially private if like with high probability, all of our like initial estimators are like approximately accurate. Then we can say with high probability, like the variance of our private estimate is going to be within a constant factor of the variance of this kind of like ideal private estimate that we could compute if we knew all of these like initial parameters. And I feel compelled for the sake of honesty to like, show you all of this part in the same way that our algorithm is not pretty, these things are not pretty, but they are kind of intuitive, and they're basically saying, if we can estimate stuff accurately along the way, then we will have an accurate final estimate. So we want our mean estimate to be accurate, and we want it like to be accurate in two ways. We want it to be like close to the true mean up to these like concentration bounds, and we also want the product of the estimate times kind of like 1 minus that estimate to be close up to a like constant factor of the truth. And this plays a role because we actually need like this expression appears in our like estimation of these like individual variances. And we also want our like variance estimator to be accurate up to a like constant factor, here 8. And I think these two are at least vaguely intuitive as to why I want like an accurate mean estimate and variance estimate. We also want D star to be well behaved. And in particular, this expression says that basically, if I were to estimate these like concentration bounds based on samples, that would be close to the true tail bounds of the underlying distribution. And sorry, this should have a star here and here. And plus some like binomial noise terms that are kind of ugly and I don't want to show. Like basically it's like saying that like D star is like a sufficiently well behaved, that its kind of like empirical tail bounds are close to its true tail bounds. And then finally, if my KIs satisfy a particular property, and you can interpret this by saying that these like KI stars are not too like dispersed, right? And so if kind of like one person has like the bulk of the data and like everyone else has 1 point, I can't really hope to like perform well here. And so this says things should be not too unfairly dispersed. So in terms of accuracy, this claim, I feel like in the sake of full like disclosure, all of these conditions are basically like reverse engineered. And so we say like if I have things that kind of satisfy all of these like constraints and I push them through this kind of like estimation process, I will then arrive at a constant factor. And so like, I'm not sure there was some kind of like, meta perspective as to why these are the right constraints, but they are certainly like a sufficient. I don't know if they are necessary. One more note is that we have some kind of like oddly specific constants here. And these come from like the constants that we're going to use in kind of our like instantiation of this result that I will show you guys next. And our constant that we get, again, again, for the sake of full disclosure, is quite large. And so certainly if you had different constants here, those would be pushed forward to be different constants. And so it's not these specific constants are the kind of absolute correct ones. Basically a different constants here will give you a different constant here. So that is that in terms of accuracy, is you basically just push all of these things through, and you see that if I have these, I'm then going to have an accurate estimate in terms of the variance. For privacy, it's actually pretty simple to see based on this horrible algorithm I showed. So we're going to have a kind of an epsilon delta here, a bunch of post-processing, and then we're going to have an epsilon 0 here. And so this entire process is going to be 3 epsilon and 2 delta dp. If you want it to be exactly epsilon delta, change your constants. So that is the framework. Any questions on that before I tell you how we kind of instantiate this? Okay. So recall, we just had to privately estimate the mean and the variance of this underlying distribution. And if we can do that, then we're done. So for this initial mean estimation, we're going to do in fact the same thing that we did in the non-private case, how we're going to take one single data point from a constant fraction of the users that have the fewest samples, and that constant fraction is going to be a 10. It's going to be a 10%, and we're then just going to compute the empirical mean of these points. And because we're only taking 1 point from each person, then we're back to looking at kind of event level privacy in this case. And so my sensitivity is going to be 1 over my sample size, and that's going to be 10 over n, and I can then just run the standard Laplace mechanism. And obviously this is going to be epsilon 0 dp, and you can prove that it also achieves all of our desired accuracy constraints in terms of what we need our initial mean estimation to achieve. Now in terms of initial variance, this one is actually a bit trickier. Fortunately, someone else did it for us, and so this is great. And so there's work, Kara Vadhan gave an approach for privately estimating variance of a Gaussian, and their estimate is going to be accurate up to a constant factor. And so we do have to slightly modify their approach because we don't assume D star is Gaussian, but effectively we're making very small changes here, and the bulk of the approach is taken directly from that paper. And the only change is we have to assume a bound on the absolute central third moment of D star, which it turns out that's important if you want to kind of ensure accuracy of their estimator. It turns out that you don't have to have a Gaussian, you do have to have this kind of specific bound. And our procedure here is we're again going to take the top log n users, and we're going to see of this of this kind of log nth user, how many points do they have? And then I'm going to take from these log n users, I'm going to take a kind of empirical mean their K points, where K is a kind of like number of points held by the user with the fewest points of these top log n, and this is to kind of make sure they're all going to have the same kind of like number of samples used as they like compute their like empirical mean. And we're then going to use these as a kind of like samples from like D star, and then we're going to apply this algorithm on these as our like estimates. And again, the kind of like accuracy requirement comes like pretty immediately from their work under this like assumption. So in fact, that's it. And it's pretty simple, in part because really like the bulk of the work here is kind of showing if you can privately estimate mean and like variance, then you can like plug this in to do this much more complicated estimation procedure. And we also kind of emphasize that if you find a better algorithm that will give you a better constant under the same privacy guarantee, then you can use that in our same framework, and you will get out like an even better constant factor approximation in terms of the variance. Alternatively, if you wanted to get, for example, like a local privacy, shuffle model privacy, any of these, you can still also privately estimate mean and variance in your preferred way, and then you can also plug those in to the same estimation framework. I'm going to talk extremely briefly about thinking about the kind of optimality of this estimator. And in fact, this is a question Adam very astutely asked at the beginning, which is that we are comparing our estimator against some thing I told you was ideal, but notice I haven't called it opt because it's not opt, but I'm just saying this is ideally how we might want to estimate things, but we can't. And we also want to ensure we have a good benchmark that we are comparing against. And so we show in the paper that in fact it is optimal up to some polylog factors. And so therefore, because we are within a constant factor of that we are also going to be within polylog of opt. And we have some extensions in the process for yeah.
Sorry, I'm trying to raise my hand. Yeah.
Oh.
How far is when you say it's optimal, are you comparing to the best differentially private algorithm or the best algorithm period? It seems that for large n at least, and maybe large-ish KIs, maybe not even very large KIs, that this would be kind of optimal, would compete with the best non-private approximation.
Yeah, so we do compare. Actually, perhaps Audra, you can say more because in fact this proof is all hers. So I believe that we're comparing against the best private opt. But if you have anything you want to add, Audra.
Yeah, we're comparing against the best private opt. I guess we haven't, in some specific cases, we can say what that sample complexity is, in terms of the KIs. And I think in those cases, we can probably say something about whether it's close to the best non-private thing. But in general, we haven't looked at that. And in fact, we need one or two assumptions on D to get this. And yeah, that is a good question, but I don't know the answer.
Thanks.
Yeah, good, thanks. Yeah. So to close, I want to talk about some kind of other like extensions that we're thinking about for this paper and also possibly beyond. One kind of like very natural one is the case where these like KIs are private, and this is kind of like one more thing that you have to kind of like estimate and respect privacy of in this whole pipeline. We're also thinking about like a personalization, which is like, you know, specifically kind of like each person knows her own PI hat, and she might receive or kind of like a privately generated estimator of the kind of underlying P. Can she use this in a JDP style to get a JDP estimate of her own PI? And in particular, she wouldn't immediately want to use this because of like a population level mean is possibly different from kind of like her own mean. But like in particular, if you have like a very small number of samples, maybe even this may be more accurate. And kind of broadly thinking about how can we apply this for doing like, you know, histograms, because effectively like, you know, every kind of like bucket in this histogram is basically just like, you know, binomial data if you're talking about frequency. And so it seems like this should extend into that case. And more broadly, user level privacy, when you're talking about either like, you know, heterogeneous quantity of contributions from each person, or in general, a large number can be challenging. And I think that we don't really understand this as much as we could. One more thing I will add to this, based on like Salil's question, is like, you know, transforming this into something that operates in a much more like, you know, federated looking environment. I think you can like squint and lie and say that it is federated learning, but it's like actually not. But it seems like this should be able to be moved into that space too. So that's all I have, and I'm happy to have questions and longer conversation as well.
Any question for Rachel?
I have more questions. So what's the obstacle to a sort of more distributed version of this? So you're saying, I'm not entirely sure I understood what you meant by moving this to a federated setting, but I guess what you mean is sort of distributed protocols to estimate each of the quantities that you're talking about?
Yeah.
And given that those things are sums, are themselves summations, like what's the obstacle? Is it the fact that the weights vary from person to person? Is that the problem, or is there anything more fundamental?
So kind of like, at least in this procedure immediately, and I'll start by saying, if you were really doing federated learning, you probably wouldn't want this exact procedure, and you might want to change some like key details of it. So kind of like in this procedure, people have to know which group they like belong in. Are you sending 1 point, or like, are you sending an empirical mean, or like, are you sending the empirical mean of some points, for the quantity of those points depend on kind of like other people's quantity of points. So it isn't like immediate, everyone send me their like empirical mean. It'd be nice if it was, but it's not. And then of course there is some other like, you know, computation happening as you do all these like, you know, estimations and the weights and like so on. And so I think in this like form as is, you can like I suppose you could call it federated learning, but there's kind of like a lot of back and forth and it doesn't really feel federated, you know? Like it is kind of like federated-esque in the sense that kind of like each person only has to contribute one single number or perhaps two ki in some function of their data, but it's not like a simple procedure that could naturally be done in a kind of like federated sense. And so I think an interesting question would be, how do we move into something that looks more natural in the federated sense, and that may require structural changes into this like estimation procedure.
I see, thanks.
Yeah.
Can I ask something?
Yeah.
So the point that you just made, that someone would have to know which group they were in, why doesn't, I've now lost track of why that doesn't come up in your algorithm in the first place. So suppose you had some, oh, I see. So suppose there was just some horrible sampling fluke and you have log n people that have very little data and n minus log n that have tons of data.
Mm-hmm.
And that's just a sampling fluke, but it could happen. So now, given that you want user level privacy, your estimates could change a lot if just one of those log n people like disappeared or was replaced by a huge number, somebody with a huge number of points. So I'm sorry, I missed how you handled that.
So we first of all say that like KIs are publicly known and they can even be like,
Okay.
yeah.
All right.
Yeah.
Thanks.
Yeah.
Sorry.
Yeah. So that's how we like handle it, is we assume they're known. And we also assume things are like not too dispersed. So we handle it by like pretending that it like isn't a problem. Hadra is like, I'm currently thinking about how to make the KIs private, and then that does become a challenge. I don't know if you want to say anything about that, Audra.
Yeah, so I think we have an assumption that pushes us out of that situation, and I think we don't really know what to do if that is the case. So it's possible you can end up in situations where like you should use the data of like the top few people and you can just ignore everyone else.
Mm-hmm.
And this framework, I think, like is not the right thing to do in those settings. And in the known and unknown case, that KI case, that's true. And I suspect that you can say that either you should do something like this, or you should use those top people and use all of their data and just have them estimate it.
Yeah, maybe you could use some kind of proposed test release to see if you're in this general framework or not. Thanks a lot.
Yeah. And we kind of like assume that we are in the case where you like cannot estimate using just like a small fraction of the users. But I mean, perhaps like a more general answer would be to have a like forking algorithm where kind of like if you are in that case, estimate on those users, and if not, then do this, and then you would kind of like always be able to like estimate something, even if that like estimation procedure is different for like different groups.
I want to ask one more question. So it seems like there are, a set of KIs that, like there should be some sort of a lower bound for the KIs, right? This is like, if all the KIs are one, you probably can't do anything, and you need certain lower bounds, and also some sort of balance in terms of who, it should be sort of the spread out among the user. Is that right? Because I didn't quite realize it during the talk.
Yeah, so that actually does appear, let me see. Here you basically have to have this condition, which kind of considers both that you have like, enough points to kind of estimate, and that things are not too like dispersed. Again, it's not clear if this is a kind of like necessary condition. You certainly need like something of this form, and like this condition we show is going to be like sufficient, but it's not clear if it's necessary as well. But you do need something like this. It's only not clear whether kind of this like a specific version of it is like the one you need, or if like something else in this kind of general family of like a constraints works.
So any other question?
Hey, Rachel.
Mark.
Are there any other any statements you can make about how biased your estimator is, even for the non-private version of it?
Yeah. So for the non-private case, it's going to be perfectly unbiased, because like as long as your weights sum to 1, it's going to be like a perfectly unbiased. For the private case, it is no longer unbiased because you are like a truncating these like a PI hats, and so you're no longer taking a weighted sum of some kind of like samples from the underlying distribution. But we can show like some like the kind of like hand-wavy version of it is a kind of like, if you estimate the tail probabilities correctly, then with high probability, the fact that you like truncate things doesn't change those like estimates, and so then it will continue to be unbiased. So like, with high probability, it will be unbiased.
Thanks. So it's the case that if you were to not do the truncation in the private estimator and all of your intermediate private estimators were unbiased, then the final thing would be unbiased.
My intuition says yes, although I'm no longer sure because we have to do a lot of these like intermediate estimations. Right. So, well, the weights would still sum to 1. So it seems like yes. Yeah. I want to say yes.
Okay, thanks.
Yeah, because so we have a lot of like estimation stuff happening in the like in the weights thresholds and like in the weights threshold and in like a computing of the weights, but as long as the weights still sum to 1, then you're just taking like a kind of like weighted average of some things that are hopefully IID samples from the underlying distribution. So yeah, modulo like truncation.
Right. Okay,
Yeah.
Thank you.
Yeah.
Are there more questions?
I had one question. Maybe it's very simple. So like, how different is this setting from the setting where I want to estimate the mean, but like weighted by the KIs? Or, like heavier weight to the heavier people.
Yeah, so we are doing approximately that. So the variance is kind of approximately weighting by the KIs, because if you have a larger KI, then you're going to have a smaller variance. So you're doing something very, very similar to that. The catch is that this kind of like relationship between the KIs and the kind of like individual variance that you use for the weighting is not exactly linear. So it's not exactly the same, but it's very, very close. If you only wanted to weight things by the KIs, then you wouldn't be minimizing variance, but you would be minimizing something probably not too far from the variance. And then you could do that without all this other like, complicated stuff, because then you could just, then you could just like weight things proportionally to their like KIs, and if those are known, then you have to do a lot fewer of these kind of like intermediate estimation steps. Yeah, because really the reason, even like in the non-private case, like the reason that you have to have a kind of like initial estimate of the mean and variance is so that you can like plug that into the estimate of the like individual variances, and that's close to K but not K.
Cool. Thank you.
Question? Okay, so let's thank
Cool.
All right.
Rachel one more time.
Thanks, Rachel. Make the usual offer that, normally the seminar comes with at least lunch and some conversation. So if you want to take a rain check on that and take us up on that at some later date, you're always welcome to drop by.
Yeah,
right.
deal. Yeah. And I will like close again with a claim that I come to Boston moderately regularly. So, I would love to see you guys in person then.
Yeah, let us know.
Yeah.
All right.
Right.
Okay, thanks again.
Sure.
Bye, everyone. See you guys next week.